So last time we were talking about probit regression. The idea of probit regression is it is a discrete choice model, but we assume that the error terms are normally distributed, right? So the Uij for each individual I, if I choose choice j, then my utility is xi j prime beta j, right? So if we take a look at a normal model, linear model, plus eij. Right. So this is the basic of a discrete choice model. Now, if we assume that the error term are normally distributed, so the eij or ei is a normal distribution, right, of 0 and sigma, where this is a j by j matrix, right? So if we assume they're normally distributed matrix, then this is essentially a probit regression. Okay. So last time we considered the case of j equal to 2. Right? So we only have two choices, A and B. Now let's go a little bit, so let's go from 2 to 3, right? So in the case of 3 dimension, if we have 3 choices, then we have 1, 2, 3, ei1, ei2, ei3. The normal distribution will become 0, and with this variance covariance matrix, okay? By the way, when I write dot here, it just means it's symmetric, so I don't write it again, right? Okay. So the first thing after we write down this model, the first thing is always that we can do some kind of surgery to it. Right? We do normalization. We have to standardize. We have to normalize the level, and we have to normalize the scale. Right? Okay. So let's do it. Sorry. Okay. So the first thing to do is to normalize the level. By normalizing level, I would turn UI1, the level 1, to 0 to use as a reference. So everything will be minus level 1 minus level 1, right? And this EI2, EI3 becomes delta EI2, delta EI3. So essentially it becomes EI2 minus EI1 and EI3 minus EI1, right? So that's the first step. Now, after minus EI1, what is the distribution of EI2, EI3? It turns out that it's still a normal distribution, but the variance covariance matrix now become distinct, okay? Right? For example, this is the variance of EI2 because of delta EI2, because delta EI2 is essentially is EI2 minus EI1. So its variance is sigma 1 squared EI1, the variance of EI1 squared plus the variance of EI1 plus the variance of EI2 minus their covariance, right? So this becomes the variance of delta EI2. Now similarly, this becomes the variance of delta EI3, and this is their covariance. So we can calculate all these from the normal distribution, right? So that's the first step. The second step to do is normalize the scale. By normalizing the scale, typically what we do is we want to normalize so that one of the variance become 1. Okay, so we fix the one of the variances. So let's make this variance 1. Okay, so has the variance covariance matrix equal to this one, right? So this is 1 here, and the variance of delta EI3 and the covariance becomes this rather ugly looking matrix, but the point is now it's 1. Okay, we fix the variance to 1. Right. So in summary, whenever we have this model like this, the first step is always do normalization. The first step is normalizing level, so one of the utility becomes 0. The second step is normalizing the scale, so the variance of one of the error term become 1. The other variance we cannot control, so we let them be, right? So here we make the variance of delta EI2 to be 1. So in the end, we have this model where the variance of delta EI2 is 1. The variance of delta EI3 is something else, right? It's complicated. And then we have the covariance matrix. Okay, so that's the two-step of normalization. All right, so let's take a look, right? After we do normalization, our variance covariance matrix becomes something like this, right? There's a 1 here. There are two parameters that we don't know. This is the variance of delta EI3. This is the variance covariance matrix. Okay, so these two are the things that we do not know, so that we can estimate from data, right? But we fix this to be 1. All right, now this is the original variance covariance matrix. Okay, so this is the variance covariance matrix before we are doing the normalization. So let's take a look at how many parameters do we have before doing the normalization. We have 1, 2, 3, 5, 6, 7. So we have 7 parameters that we can supposedly estimate before doing normalization, right? But it turns out that we cannot really estimate all of them. There's no way to identify them from the data because we need to do normalization. And after doing normalization, we find out that there are only 2 free parameters to estimate. So we have reduced the number of parameters from 7 to 2. Okay. Turns out that only 2 parameters can be identified, not 7. All right. Now, in general, if you take a look at do the math, in general, if there are j alternatives or j classes, at most we can estimate 1/2 of j minus 1 minus 1. Okay, at most we can estimate this amount of parameters after normalization for the variance covariance matrix. Okay, so for this variance covariance matrix, there are j times j elements, but at most this is the amount of elements we can actually estimate after normalization. So let's say j equal to 3. If j equal to 3, then out of the 3 by 3 matrix, how many parameters can we actually at most estimate or identify? It's actually 3 times 2 divided by 2 minus 1, 2. Okay, so at most we'll be able to estimate identify 2 parameters from the variance covariance matrix, which will be these 2, right? Okay, just like we did here. All right, so that's some normalization exercise for j equal to 3, and if you want to do j equal to 4, 5, 6, it's exactly the same rule, right? So let's take a look at some example. Okay, so now suppose we have some data, and the data is on brand for ketchup. I hope people know what ketchup is, right? So there are 3 major ketchup brands. Heinz, Hans, and Delmont are 3 major brands that occupy the ketchup market. Now, oftentimes many supermarkets would produce their own ketchup, so we call them the store brand. All right. So basically, we have 4 different types of ketchup. You can think about it that way, and the data is on what people buy. Okay. The variable here is the price of each one. Okay, and the income of the buyer. And the brand they actually purchase. So for example, right, so this is 2 kinds of data. For here, if the price of Heinz, Hans, the amount, and the store brand, so this is store brand. So if the price is 1.46, 1.43, 1.45, and 0.99, if the price are these 4, and if the income of the person is supposedly $44,000, I believe, then this person chooses the store brand. Okay, so now if the price changes, maybe because this data is collected at a different time, or maybe because this is collected at a different store, right? When the price changes, somebody else, this person, will choose Heinz. Okay, so we have a bunch of data on the prices of all the ketchup being sold at different stores at different times, and then we have data on many individuals of very different income and what do they buy. Okay. So our goal is to predict or to model individual choice in this case. All right. So here you can see that what is this price variable? We talk about there are 2 kinds of variables we can have in discrete choice models. The first one is a individual specific variable, which in this case will be income. So income is individual specific because it only varies with individuals, right? So so for income, it's only a variable of I. All right. It only varies with individuals. Now, for price here, okay, it's actually a variable of ij. It varies both with I and a j, meaning that, for example, different brands have different price, but also different people face different prices presumably because they go to different stores or they go to shopping at different times. So different people also face different people here in terms of different I here also has a different set of prices. So price here is ij. Now this is what we call alternative specific. Or if you want to be more specific, you can say it is both individual and alternative specific variable. Okay? All right. So what is our model, right? Now this is the first model we can write. We can say uij is equal to alpha j times delta price ij times gamma j income I plus ei. All right, so our utility varies with, so the individual utility varies with price, and varies with income. Okay? All right. So one thing here that we should note is why do we have why do we have gamma j? Okay. Can we just do gamma here? So it's gamma times income I? The answer is no. So if that goes back to our last class, right? Whenever the variable is is individual specific, the parameter has to be alternative, has to vary with alternative. So the parameter has to be something like a gamma j. You cannot have gamma. Because if you have a gamma and income I, then essentially that's the same thing for each alternative. So it's basically a constant for each alternative, then it's useless, right? So it has to be gamma j here. What about this this delta j? So what about this delta? Can we have delta or can we have delta j? Right. So for the delta, that is the parameter before price, should it be constant, or should it vary with the alternative? When we talk about a parameter, we say if a parameter is a constant like this, we say it is generic, and then when this parameter varies with the choice, whether it's j, we say it's alternative varying, right? So it's not generic coefficient. Okay, so should this delta be delta or delta j? The answer is both. Okay, we can have it to be delta or we can have delta j. This completely depends on you, right? So it's up to the modeler to decide. But for this one, it has to be delta j. Sorry, it has to be gamma j. Okay, this one we can have delta or delta j. When we have the delta j, it means that the effect of price on the utility varies for different choices. Okay, so maybe for example, economically this means, for example, if I purchase the amount, right, we have 4 brands. If I purchase the amount, the price of the amount matters more to me. So I care more about the price of the amount. And then when I purchase if I purchase store brand, the price of store brand matters more to me. But if I purchase the amount, the price doesn't matter that much to me, right? If you say delta, if you make this delta vary with j, that's what's going to happen, which means your model is assuming that price matters to me differently, depends on which brand. Is it a reasonable assumption or is it not? So you can judge for yourself, right? Here we start with a model in which delta is a constant. So doesn't matter, okay? It doesn't change with j. If it doesn't change with j, it just means that price, regardless of which one I buy, price has the same importance, right, to my utility. Okay, all right. So if we want to do this in R, we can use the mLogit package, and there is a function called mLogit which is used for doing this probing regression, right? And the syntax is a little bit complicated, in a sense. But you can see that for mLogit, the syntax is y as the response variable, and then the x variable really is divided into three different kind of x variables. The first kind of x variable is called alternative specific variable with generic coefficient. All right. Let's see. Where's okay? There we go. So if you want to do it, what is the alternative specific variable? Something like, right? So if Zij, if Z varies with I and J, that's the alternative specific variable. And then with generic coefficient, meaning that the coefficient does not change with J, okay? It's beta Zij. Now if this is in your model, if Uij is equal to this, then we put this here in the first part of the formula. The second part of the formula, the second type of the x variable is individual specific variable. So individual specific variable is something like Si, okay? So it only changes with I. Now for Si, the coefficient, the parameter has to vary with J, okay? So you don't have to talk about that. Now the third part is a third kind of variable is called alternative specific variable with alternative specific coefficient, meaning something like this, okay? Meaning Wij, so it's alternative specific variable, but then the parameter let's say the parameter is called alpha, okay? The parameter also varies with j, okay? So in that case, this is a alternative specific variable with alternative specific coefficients. So the formula, in order to use this m-logit function, you need to think about what type of variable you have and what type of parameter you have. In our model, the price is a alternative specific variable with a generic coefficient. So we put the price here, okay, which is the first part. Now, the second type of variable we have is income, which is a individual specific variable. So we put income here. The formula says you have to separate them, right? So put income here, indicating it's the second part. There's no third part here. We have no alternative specific variable with alternative specific coefficients. So we just ignore them, right? So that's how we specify this formula using this function. And here are the results, okay? It turns out that, we have 3 intersects, and then we have a price, and then we have three coefficients for income, okay? All right, so these are one of our main estimates for the model. If we go back to this model, let's take a look. How many coefficients do we have? Well, for each j, we have an alpha j. So we have 4 choices. I'm sorry, right? So we have 4 choices. So we should have 4 alpha j. However, one of the choice is becoming the reference level, right? So we set them to 0. So in the end, we only have 3 different alpha. Okay. And which one is being used as a reference? The amount times Hence. So it looks like we use store brand as the reference. All right. Okay. But actually, I say here, right? Ref level equal to store brand. So I set store brand equal to the reference level. So there's no store brand here. So these are the 3 alpha. And then for income, we also have 3 coefficients. Okay, corresponding to gamma, the amount, Heinz, and Hans. Okay, because store brand is again set to 0. So for income, we also have these 3 coefficients. Now, how do we read them? For example, it says 0.18 here for Heinz. It means that if your income is higher, if you have higher income, you are more likely, or your utility for Heinz, you are more likely to buy Heinz. But what do we mean by more likely? It means more likely with respect to or relative to store brand. So all 3 of them has positive coefficient. It means that when people's income higher, they're less likely to buy the store brand, right? Because all of them are with respect to the store brand. Finally, for price, there is only 1 coefficient. It's negative, right? -3. It means when price is higher, people buy less. But there's only 1 coefficient. Why? Because the coefficient here for price is a generic coefficient that does not vary with j. So we only have 1, okay? 1 delta here. All right. What are our estimates for the covariance matrix, variance covariance matrix? Remember, we have 4 choices here. For 4 choices, how many independent coefficients can we identify from the variance covariance matrix? Well, let's see this formula, right? So now j equal to 4, we have 4 choices. So 4 times 3 divided by 2 minus 1. So it looks like it's equal to 5, okay? So we should have 5 variance covariance parameters we can estimate after normalization. And here we are, okay? Here they are. All right? So these 5 are what we can get by estimating the variance covariance matrix. So from these 5 estimated parameters, we can construct the 4 variance covariance matrix here. Okay? So this is our construction. Now, this is a better way to write it, right? So now our variance covariance matrix is essentially the amount, Heinz and Hans, are normally distributed according to this normal distribution of 0 and with this variance covariance matrix. So this is already after normalization. Okay? Now after normalization, first of all, we have 4 categories. We have 4 different classes, but we set store brand to be 0, so we end up with only 3, right? And the variance covariance matrix for the 3 variables always has a 1 here. Why? Because we always normalize the variance of this option to 1, because we fix the scale, right? Okay? So in the end, how many free parameters do I have? 1, 2, 3, 4, 5. So these 5 are the ones I estimate using the probing model. And so the utility is here, okay? So all these numbers are taken from our estimation results. So how do we, what does it tell us? It tells us that if your income is higher, okay, it has the highest, the utility of the amount increase the fastest with income relative to store brand, okay? And, Heinz, all right? So Heinz has when income is higher, the utility for Heinz increase the fastest relative to store brand. What else can we get from the results here? If you look at the variance covariance matrix, it looks like the Heinz and the Hans are positively correlated, their utility. The utility, and they're negatively correlated with the amount. And that means people who are more likely to buy Heinz, people who buy Heinz are more likely to buy Hans. People who have Hans are more likely to buy Heinz, but not so much for the amount, okay? And all of this is actually relative to store brand. So you can think about Heinz and Hans as closer substitutes because they are positively correlated with each other. They are more like each other, okay? And if you look at the results here, it's also pretty obvious. When income becomes higher, you are more likely to buy Heinz, and you are more likely to be Hans, significantly, right? You're not so much more likely to be the amount. So it looks like the amount is the cheaper. Now, typically, store brand is the cheapest in any supermarket, right? And it looks like that the amount is also a pretty cheap and a closer substitute with store brand. And it looks like the Heinz and Hans are the sort of like the premium, high-end brands that are more substituted with each other. So they have positive correlation here, negative correlation with the amount. And when your income becomes higher, you're more likely to buy one of these ones rather than the amount or the store brand. Right? So that's what the results tell us. Okay. So you can see that once we do a probing model, the variance covariance matrix can tell us something about how close or how substitutable these different options are, conditional on your x. Okay, right? So conditional on x, if the two choices are still very much substitutable and they are correlated, then it shows up in our estimate as a positive correlation in the error term. Right? Remember, so that brings us back to the discussion when we talk about the IIA problem, where remember the blue bus red bus problem. The blue bus red bus problem is a problem for logistic regression, because in logistic regression, as you will see very very shortly, it's we only explain the choice using the x variable, right? We do not allow a covariance matrix like this, that we do not allow the different choices to be correlated. So when I was explaining the red bus versus blue bus example, I said the fundamental problem is because there may be some unobserved variable, okay, that explains people's preference for bus versus car. Or in our example using the subway, car, and a bus, I said there may be some unobserved variable out there, such as people's preference for public transportation, that would make bus and subway more correlated with each other, rather than with car, right? So this unobserved variable here is the error term, right? So we're using the probing, the error term captures such unobserved variable. So let's imagine we're not doing the amount Heinz example. Suppose we use probing to estimate the transportation example, right? Using the transportation data, the bus, car, and the subway data. If we use the probing model, then the error term would capture things like preference for public transportation, okay? Because preference for public transportation is an unobserved variable in that example, which makes bus, suppose bus and the subway more correlated, positively correlated with each other, and then make bus and the subway and a car, and make bus and a car negatively correlated with each other, right? So the error, because you should think about this error term as capturing the underlying unobserved variable that makes some choices more substitutable with each other, and make other choices not so substitutable with each other. Okay. All right. What other model we can do? Like I said, we can specify this delta to be generic or we can specify this delta to be also alternative specific, meaning it varies with j. Right, so model 2 will be something like this, where I let this delta also varying with j, so that price has a differential impact on different choices. Now, if we want to do this using the M logic function in R, so like I said, now that if we specify this model, then we have an alternative specific variable with an alternative specific coefficient. So in this case, we should move price from here to here, because that's how that's the rule of the formula. And then we actually now we don't have anything here, so we just put a 0. That's just how the function works. If we look at the results now, price no longer has only one coefficient. Now price has 3 coefficients as well, right? And in fact, price should have 4. Yeah, there are 4 prices, there are 4 coefficients. I will explain why 4, but the reason why there are now different coefficients for price is because we allow the delta to vary with the j. So what does it say? Look, what does the result say? It says that if price has a differential impact on how likely people are going to consume each brand, looks like the effect of price on store brand Heinz and Hunt's are almost the same. But for the amount, people are not that sensitive to price. Okay, when price increase, it looks like they don't respond that much. You can think about it as saying the elasticity that people have with the elasticity of demand for the amount may be a little lower, okay, than the elasticity of demand for the other brand, right? So why are there 4 parameters rather than only 3? Well, that's because if you set this delta to delta j, and if you normalize the level, it's actually impossible to normalize the first one out. Okay, so let's see. Now, if we have a model like this, UI1 is equal to, let's say, delta gamma 1 income y, and UI2 is equal to gamma 2 income I plus EIJ plus EIJ. Okay. Now, if you have that, then notice that this is all income I. So when I normalize the level, I can make this whole thing equal to 0. So this becomes the gamma 2 minus gamma 1, right? Times income I plus the delta Ij. Okay. So it becomes a model where this is 0, and this has only one parameter to estimate, because this is only the parameter for income I. Okay. So now, in this case, if our parameter is a individual specific variable, then after normalizing the level, I end up with only one parameter to estimate, not 2. However, if we have something like this, right? If we have a delta 1 price 1 price I1, right? Ij plus Eij, and delta 2 price I2 plus Ei1, Ei2. Okay. Now suppose we have something like this. Well, first of all, let us make the variable generic, okay, not alternative specific. What I can do in this case is also I can set the whole thing to 0, so that the second level becomes what? Becomes delta price I2 minus price I1, right? Okay. Right? Time plus the delta E. Now, so now what I'm doing here is I essentially I have a different x variable. So the x variable becomes, instead of price Ij, it becomes delta price Ij. But I also only have one parameter to estimate. Okay? So we end up with only one, right? However, if our model is delta 1 here and delta 2 here, so this is the case where our variable is alternative specific and our coefficient is also alternative specific. In this case, if I normalize the level, it doesn't help. Okay? I can set this equal to 0, but the level 2 will still be delta 2 price I2 minus delta 1 price I1. plus delta E. In other words, in this case, there are still two parameters to estimate, not one. Okay? So it's impossible to get rid of one of them. So, so that's the reason why you see 4 parameters, not 3. Because when when the x variable is alternative specific, and the coefficient is also alternative specific, then you cannot really delete one of them, right? So there are 4 here, but for income there are only 3, because income is individual specific, and we can get rid of one of them. Okay, when we do normalization level. All right. Okay, we end up with a very similar, a little bit different results than before, mainly because the amount has a smaller response to price. But otherwise, the correlation structure is exactly the same as before, which shows that 2 of them are more correlated than the other. Okay. All right. So that's a little exercise in probability regression, which we're going to use to estimate people's demand for different brands of different products. And the benefit of probability is that it allows us to have an error structure that is correlated with each other, so that if there's any unobserved variable that makes some choices closer to each other than other choices, we're able to capture that. Okay. Now let's consider a different kind of distribution. Remember, when we go back to probit, long way back. Okay, so like I said, probit is a kind of discrete choice model. The defining feature of probit is the error term is assumed to be a joint normal distribution, but we don't have to have this joint distribution. Okay, we can change the distribution to some other kind of distribution. So if we change it to some other kind of distribution, then that's no longer probit. That's the other kind of model, right? So let's try. What if I do uij is equal to xij prime beta j plus eij? Now, instead of assuming that eij is a normal distribution, a joint normal distribution, I'm going to assume, I'm going to get rid of the normal distribution. I'm going to assume that eij is distributed according to a gumbo distribution. Okay, gumbo 0, 1. Now, do people know what gumbo looks like? So gumbo is a special type of distribution. It's also called, there's a special name for it. It's called extreme value distribution, okay? Type 1, because there are different types, right? So type 1 is gumbo. I can assume, so I'm going to introduce a new kind of model, right? Not probit anymore. A new kind of model where exactly the same discrete choice model, but I'm going to assume that the error term are distributed according to a gumbo 0, 1 distribution. Okay. Now, where's the variance covariance matrix? There's no variance covariance matrix because I assume that the error term are all independent. Okay, so they're IID distributed according to gumbo. Right. So why do I do that, right? So that's a different kind of type of model. What is the feature of this model? Well, the first feature of this model is that it actually looks very much just like the probit model, because the gumbo distribution is actually very close to the normal distribution. It looks almost like the normal distribution, with the exception that the tail is more heavy. Okay, there's a fat tail out there. Let's take a look at what gumbo looks like. Okay, so this is normal 0, 1. This red thing is normal 0, 1. And this blue thing is the gumbo 0, 1. And you can see that on the right-hand side, the tail, right, the tail here is fatter, right? There's a heavier, fatter tail than the normal on this part. Okay? So, but overall, they look very similar, except the heavier tail here. And in fact, the heavier tail here explains the name that why gumbo is called extreme value. I think about the reason why it's called extreme value because it could be a distribution that could be used to describe very normal distribution like a variable, but sometimes this variable can suddenly take on, more extreme values. Right? So think about, when you are modeling the financial market. In financial market, right, oftentimes it's pretty normal, but then we have many extreme events happening, okay? So if you want to model these sort of extreme events happening, you can use a Gumbel distribution where essentially there are heavier tails here, so it's more likely to have these large values, right? So that's where the name extreme value distribution come from. But that's not our purpose here. Here we use the Gumbel distribution, but we note that the Gumbel distribution actually looks very much like the normal. Okay, they're pretty similar except the heavier tail. So why do we use Gumbel distribution? Well, and by the way, this is what it looks like. Okay, so this cumulative distribution function, the CEF for the Gumbel, looks something like this. And this mean, so this is the expectation, this is the variance. Okay, so you can take a look. Now, if we assume Gumbel distribution, what happens? So that's the question. Okay. Well, the first thing that we should do, I would say the first thing I should note is because Gumbel looks very close to normal, using Gumbel distribution and using normal distribution are actually almost identical. So why do we do that? Let's say Uij is equal to Xij prime beta j plus Eij, right? Now, assuming Eij IID Gumbel, okay, is actually very much similar to assuming Eij IID normal, because these two distributions actually look very similar to each other, right? So if we assume it's IID normal, what kind of model is it? Is it probit? Not exactly, because probit does not assume IID. Probit allows different choices to be correlated with each other. So in other words, probit assumes a normal distribution with a variance covariance matrix where the where there's covariance, right? But if we assume it's IID normal, okay? Suppose we assume it's IID normal, what kind of variance covariance matrix do we have? We only have variance 1, variance 2 square, variance 3 square, but everywhere else is 0, right? So if we do not allow any covariance, that's an IID normal. Now, if instead of using the IID normal, we use IID Gumbel, then that basically is our model here, okay? So the key difference when we use this Gumbel distribution and assuming it's IID, it's actually very similar to an IID normal model. But it's not probit, because probit allows a variance covariance matrix, allows them to be correlated, but the IID assumption doesn't, right? So that's the first thing. The second thing is, why do we use Gumbel anyway, right? So why do we just not just use normal? Because Gumbel brings us additional benefits. Right? The benefit is this, okay? The benefit is, once we assume the error terms are Gumbel distributed, we have a closed form solution. Closed form, meaning that the probability, okay, the CCP, the conditional choice probability now has a specific expression that is very easy to calculate. So mainly we use Gumbel for convenience, if you will, okay? So it turns out that the probability of y equal to j conditional x, if we assume the error term are Gumbel, has a very nice formula that's very easy to calculate. If you use normal, we don't have this formula. But if you use Gumbel, we have a very nice formula. Let me show you what this formula is, okay? So, let's begin with Uij, the utility function, right, is equal to Xij plus beta j. Let me actually write it. Let me just say Vij, okay? So remember, so Vij is equal to Xij prime beta j, just for convenience sake, all right? So Vij plus Eij. And now I'm going to, so in this case, what is the probability that y is equal to, suppose we only have A and B, okay? Suppose we only have two classes. So in this case, I only have UIA and UIB, right? What is the probability that I will choose y equal to b? Conditional, okay, let's just write this. Rather than x. What is the probability? Well, it's basically the probability that VIA plus EIA is smaller than VIB plus EIB, right? Okay. Now, what should I do after this? Well, notice that if we have these two classes, right, A and B, two classes, then I should also do normalization, okay? So we have EIA, and then UIB is equal to VIB plus EIB. So I should still do normalization. So let me make this 0, okay? So now this becomes what? This becomes delta VIB, and this becomes delta EIB, all right? Okay, so now the probability of choosing B relative to A will be the probability that delta VIB plus delta EIB is larger than 0, okay? Right. Which means what? Which means this is equal to the probability that delta EI, I'm going to write EIA here. Let me explain, okay? Delta EIA is smaller than delta VIB. What is delta EIA? Delta EIA is EIA minus EIB. Delta EIB is EIB minus EIA. So delta EIA is basically the minus of delta EIB, okay? So, right? So we can write this way. Okay. Now, what is this probability? It turns out that if this is a normal, if EIA and EIB are a normal distribution, then this is simply a normal distribution too, with mean 0 and a variance for covariance matrix that, you know, and a variance equal to sigma 1 squared plus sigma 2 squared minus sigma 1 2, right? So this is the case when it's a normal distribution. And in the case of normal distribution, there is, you know, this is where we stop, because there's no formula for no convenient formula to calculate that, okay? But however, if it is a gumball distribution, then turns out that if EIA and the EIB are gumball distribution, then the delta EIA, okay? So the delta EI, so EI1 minus EI2, has a very nice CDF, cumulative distribution function. The CDF look like this, okay? So the f of delta EI is actually equal to exponential delta EI over 1 plus exponential delta EI. So in other words, if I let z equal to delta E, where E is a gumball distribution, then the cumulative distribution function of this z variable is simply EZ divided by 1 plus EZ. What does this remind you? This is the sigmoid function, right? And we also, so that's why this z, you know, the delta E is called logistic distribution, okay? Now, we just give it this name because exactly the CDF look like what? EZ 1 plus EZ, right? So, what is the formula here? Well, this is a logistic distribution variable. So the probability that this delta E is smaller than this is simply e to the delta VIB divided by 1 plus e to the delta VIB. Okay? Right? Can write this. So it turns out that the probability of choosing y equal to b is equal to the sigmoid of delta VIB. Right? So what is this model? This is the logistic regression model that we have all studied. Okay? So right? So it turns out that from the utility, from the discrete choice model, you know, it turns out that if we start with uij equal to xij prime beta j plus eij, and if we assume that eij is a gumball distribution, then this model is exactly equivalent to a logistic regression model, because we have the same expression for the CCB, for the conditional choice probability. So we arrive at the logistic regression model. Okay. right? So we have basically talked about two kinds of model here, right? We start from the discrete choice model, and we say if the EIJ are normal distributed, joint normal distributed, it's a probit. Now what I've shown you is if this EIJ is IID gumball distributed, then it's a logistic regression. Okay. So what does it mean? It means because we have already studied logistic regression. Why do we need a different kind of way to introduce logistic regression? It's because if we introduce logistic regression this way, it gives us additional insight into how logistic regression work. And also, so that's the first point. The second point is now we also have some kind of economic interpretation of the utility interpretation of the results of logistic regression. So let me first say the first point. Think about the difference between logistic regression and a probit. What is the difference between logistic and a probit? Using this framework, we can see that the difference is logistic regression assumes IID gumball, and a probit assumes joint normal. But like I said, gumball and a normal look very much like each other. They're very similar in terms of distribution, right? So that's actually not the major difference. The major difference is not between gumball and a normal. The major difference is between this IID assumption and the joint assumption. For probit, we allow different choices to be correlated with each other, the error terms to be correlated with it into a variance covariance matrix. Right? We allow them to have covariance not equal to 0. For logistic regression, the error term has to be IID, meaning different error terms are independent of each other. There's no covariance. Okay? Covariance equal to 0 for all the choices. That's actually the key difference between logistic regression and a probit. For logistic regression, we assume that each choice, the error term of each choice, is completely independent of each other. That's the main difference. And that explains, the blue bus, red bus phenomena, right? That explains the IIA problem. The reason why logistic regression has the IIA problem is because it doesn't capture any unobserved variable that make different choices correlated. Because logistic regression essentially assumes the error terms are independent. Okay, so that's the key message you should take from this discussion. All right. By the way, this difference between logistic and probit only happens when we have more than 3 choices. Okay. If we have 2 choices, okay, just 0, 1, or A and B, right? If there are only 2 choices, then what is the logistic regression? Logistic regression is UI1, UIA, okay, is equal to 0 because we can always normalize to 0, and UIB is equal to Xij beta j plus XIB, right? Well, UIB plus plus EIB, but this EIB is really the original, right? So this really the original EIB minus EIA, right? Okay, so I should say E tilde IB, okay, because we have normalized 0, right? So for logistic regression or for probit, if we only have 2 classes, then we always normalize 1 to 0, and the other one becomes this one, where the E is the difference, right? So for logistic regression, this E is the difference between 2 gumball distribution. For probit, this E is the difference between 2 normal distribution. Okay, but like I said, the normal and the gumball are very much alike. So if we estimate the logistic or the probit on 2 classes, we almost always get exactly the same result, exactly the same fit, right? It's only when we have more than 2 choices, okay? If we have, like UIC, if we have 3 classes, then they are different. Because once we have a UIC, we have something like XIC prime beta C plus EIC, right? It's in this case, we can talk about the correlation between EIB and EIC. So in this case, the logistic regression assumes that these 2 random variables, these 2 error terms are independent. But probit allows them to be correlated. If we have more, like if we have D, okay, E, if we have more classes, then the probit allows all these classes to be all correlated with each other. So we have a large variance covariance matrix. But logistic regression essentially assumes that all of them are independent. But if we only have 2 choices, okay, then there's nothing to talk about. Okay, there's no covariance, or there's no correlation to talk about, because there's essentially only one E left after normalization, which means that when we're talking about two class, a binary choice, then logistic regression and probit are essentially the same thing. They always give you almost exactly the same result. All right. So let's see. Okay. Now let's take the probit model, for example, to a binary problem. Remember we did the income versus voting problem earlier, right? I'm using income to predict whether a person vote or do not vote. So this is the binary problem. And if we do the probit, one of the first things is what about we can take a look at the estimate for income and intercept. Now this estimate is going to be the parameter estimate is going to be different from logistic regression. However, the fit is going to be exactly the same. Okay, so one is logistic, the other is probit. They are almost exactly the same. Meaning that when you are doing a binary problem, just use logistic, never use probit, because logistic regression is much faster to compute, right? Because we have a formula for the probability. For probit, there's no formula. It's a normal distribution. There's no closed form solution. So probit is slower to compute than the logistic. So for binary, always use logistic and never use probit because they're always the same. I've seen many people who are unfamiliar, right? They're writing a paper and the y variable is binary, and they say, okay, let me do a logistic, let me do a probit, let me compare the results, and this is a very bad practice because they're always the same, right? But when it comes to 3 and more classes, then probit and logistic become truly sort of different, give you different results. Probit being more flexible allows the variance covariance matrix to be estimated, but it's also significantly slower than logistic regression, and harder to estimate because logistic regression has this closed form expression for the probability which we can directly compute. For the probit we don't have, right? So I have to numerically compute the normal distribution. Okay, all right. So. And by the way, like I said, there are two benefits to writing the logistic regression in terms of discrete choice model or random utility framework. Using the random utility framework, first of all, it gives us this insight into logistic regression as equivalent to assuming the error term being independent. So that's the first benefit. The second benefit is now we can, if we use the random utility framework or discrete choice model, we can give the results of logistic regression and the results of probit regression a utility reading. Okay? So like I said, the discrete choice model, uij equal to xij prime beta j plus eij. Like I said, you can think about this almost as a structural model because there's an underlying, it's almost an economic theoretical model out there, right? It says, how do people make choices? Well, people have different utilities. And then the y, which indicates what choice people make, is simply the argmax of uij, right? So this is almost an economic theory kind of model. So it's the simplest structural model we can have. So if we estimate the discrete choice model, what does the estimate tell us? Well, the estimate tells us people's utility, okay? Right? So if we believe in this model, then our estimate tells us something about the utility that people have. And that's a very nice thing, right? We can then using this utility, what can we do? Well, in economics, we can do, for example, normative exercise. Right? So previously, if we do not use the random utility framework, if we simply treat logistic regression as a statistical model, not an econometric, not a structural model, if we only treat it as a statistical model, then the only thing we can do is to fit our data and then using our model to make predictions, right? But if we're willing to treat it as a structural model, then the estimate tells us something about the underlying utility of people. And then based on this utility, we can make not only positive analysis, but also normative analysis. When in economics, normative analysis is simply meaning that we can make welfare calculations, right? What is people's utility when they do this? What is people's utility when they do that? Based on our estimate. And that can be very powerful, right, in economic analysis. So let's give you, so here's one thing that you can do. suppose we say that this xij is people's observed variable, right? When people make decisions, they see xij, but they do not see. Let's say this, okay? Let's say this is time, right? Now, this is when people make decisions. You make choice here. However, you observe xij first, and then you observe eij later, and then you make choice. Okay, suppose that's the case. So eij comes after xij in terms of time. You can think about eij as a shock, a random shock that people receive. So xij is. Suppose I want to use this model to explain, for example, people's choice of their jobs. Okay, so so uij will be a different. I'm sorry. Let's stick with the consumption example. Suppose we use this model to explain whether people will buy their amount. Okay, ketchup, their amount, or Heinz. Which brand do they purchase? Xij will be the price and other things, okay, that you already know before you walk into a supermarket. The eij could be something like your taste, or your mood. Okay, so today I feel happy about the amount, or tomorrow I feel, hey, maybe I like Heinz more. So eij is like your random taste that you do not even know before today, right? So eij is like a shock. Now, if we give this interpretation to the model, then we can calculate people's expected utility before they receive the shock. Now, after they receive the shock, they make the choice. We can calculate their utility, which is the realized utility. But before the shock, we can calculate their expected utility. And this expected utility has a very nice formula if we assume the Gumbel distribution. Okay? If we assume the Gumbel distribution, then the expected utility, this EU thing, which is the utility before receiving a shock, is simply the log sum of e to the xij prime beta j. Okay, that's it. And j from 1 to j. So log sum exponential. This becomes our expected utility. Okay, so there's a very nice formula that we can easily calculate expected utility if we assume the Gumbel distribution. Okay, let's see some application to that. All right, application for that. By the way, you can always plus c here. Okay, you can always add any constant to the expected utility. It's the same thing because in the end we can only fix the difference between the utility of different options. We can never fix the absolute value, right? So we can always add minus constant, but that doesn't matter. Okay. All right, so let's see some example, okay? Let's use our model, discrete choice model, to estimate people's choice of their employment. All right, so this is the employment example. Now, people can work in different sectors. So manufacturing sector, retail, education, health, etc. Right? People can work in different sectors. And we observe some individual variables, like their gender, their education, and we also see their wage, right? So this is our data look like. People's gender, their education level, and their wage, their current wage, and the sector they're currently working. All right. So what I'm interested. Well, let's first take a look at the data. Okay. So this is using US data, and you can see that the majority working in manufacturing and the professional sector. Health sector is also huge. If we look at the wage, the mean wage, then it looks like professional sector has the highest wage. Retail sector, which is where people sell little things, the retail sector has the lowest wage on average, right? Manufacturing has the second. Personal sector, personal service has the second lowest wage out there. In terms of distribution of gender, then most of the time, if you are manufacturing, the professional sector has the highest percentage of male. On the other hand, the education sector has the highest percentage of female. Right. And if we look at education level, professional sector, again, has the highest education level, the lowest one being personal and the retail, right? Okay, so, so that's some basic data. And what I'm interested in doing here is I'm interested in estimating people's choice of which sector do they work in, based on their education and based on their gender. Okay. So what is my model? Well, my model is this. Uij, the utility of working in different sectors. So J now is sector. Okay. The utility of working in different sector is this alpha j plus beta wij. Wij is the wage you would receive in different sector, right? And plus eij. So that's a very simple model. This model just says, okay, you are choosing which sector to work in depends on your expected wage, okay? Your wage in the expected wage you can receive in different places, plus a random shock to your random utility that we do not know. And I'm going to assume this random utility is a Gumbo 01, okay? And by the way, why the Gumbo 01, the 01 has fixed variance. Why do I fix the variance of Gumbo? Well, because I can always do that. Because we can always fix the scale, right? So here, when we do logistic regression, when we do probit, we fix the scale by normalizing the variance of one of the choices to be 1. For logistic regression, there's no need to do that because we start by assuming Gumbo 01, meaning the variance is already fixed. Okay, so you no longer have to do. You only need to normalize the level, and that's enough. Okay. Now, the problem with wage Wij is that I do not actually see people's wage for different sectors. I only see, if a person works in this sector, I only see his or her current wage. I do not know what the expected wage would be if that person moved to other sectors, right? But I can predict that, okay? So I can predict the person's expected wage based on their education and gender. And I'm going to use the education and gender to predict the expected wage people will receive. And then using that expected wage, predicted expected wage, I'm going to fit this logistic regression model. All right, clear? It's very simple, okay? All right. Here are the results, all right? I'm going to run a simple logistic regression model of sector on wage, but this wage will be my predicted wage that people will receive in different sectors. And here are my results. It's an extremely simple model where the alpha, the intercept, varies for each sector. So the intercept could, in this case, could be interpreted as people's mean utility without receiving any wage. Okay, mean utility for working in that sector. Okay, and the wage has the estimate of 3 point. So what this means is that when wage is higher, then people are more likely. Hold on. Okay. So here the wage is a generic coefficient. I do not allow it to vary by sector. I could, okay, but I said this. But I said a generic coefficient. So this really means if wage is higher, then people are more likely to work in that sector. But the response is always the coefficient is the same. And these tell us about the people's mean utility of working in different sectors. So it looks like that people like to work in health, okay, relative to the other ones, right? What is the reference level? Health, manufacturing, personal, education. Okay, right. So education is the reference level. So compared with education, health is more preferable to education. For whatever reason, retail is also, but professional is less than education, etc. It's we can read about it into it. Okay, all right. So one thing so once we have estimated this model, like I said, if we believe in the discrete choice model, then we can give our estimate a utility reading, right? So we can say, okay, the estimated coefficient reflects people's utility. Now, which means that I can also calculate the expected utility, EU, right? The expected utility of people before they receive the shock, the random shock E, when they make their choices. And the expected utility is like this, okay? Is log exponential alpha j plus w beta wij. All right. So here's what I'm doing, okay? I calculate the expected utility, and for everybody, okay, for all the people, because remember, people vary in their education, and people vary by their gender. So different education and gender combination have a different expected utility according to my results. All right. So here are the results. This is the summary statistic. U is my calculated expected utility using the log sum exponential formula I just saw, okay? All right, so now if we believe in this, if we believe that our model tells us something about people's utility, all right, and then tell us about how people actually make choices, then I can make counterfactual predictions. Remember, counterfactual predictions can only be made if we are typically can only be made if we are doing a structural estimation, meaning that our model has a structural economic reading into it. So here, if we treat our discrete choice model as a simplest structural model, then we can use it to do some counterfactual prediction. Here, the counterfactual prediction I'm going to make is what happens when there's a 20% decrease in manufacturing wage. Okay, so this could happen in many ways. A typical scenario would be, suppose there is, which people have already done this. Okay, people in the paper have already done that when they analyze trade, for example. When a country like the United States face trade liberalization, right? When the U.S. start to trade with China, for example, and because China has this high advantage, big advantage in comparative advantage in manufacturing at the beginning, right? So many jobs will move to China, and especially because China had produced many very cheap goods, so the U.S. manufacturing sector will suffer. So the wage in the U.S. manufacturing will decrease, right? So let's assume, okay? Let's imagine what happens when suddenly the United States open trade with China, and suddenly there's a 20% decrease in manufacturing wage because of this competition with China, right? What happens? Well, back to the data, okay? What we're really saying is the manufacturing wage, okay? The manufacturing wage here will all suddenly decrease by 20%. If this happens, I want to predict what people's choice will be in that scenario. That's called a counterfactual simulation because that's a scenario that has never happened in our data, right? But I want to predict what will happen, okay? So here's the prediction. Very easy. How do we predict? Well, we already have our discrete choice model, right? We already have our estimated discrete choice model. So all I need to do is make manufacturing wage decrease by 20%, and then predict people's choice using this discrete choice model. It's very easy, okay? And here are the results, all right? I change the manufacturing wage, predict the results again, and here is the resulting sort of employment share of each sector. You can see that manufacturing share, the people who continue to work in manufacturing now is 16%. Before this 20% decrease, if we look at our original data, originally manufacturing has 21% share. So 21% people work in manufacturing. After this 20% decrease in manufacturing wage, only 16% people will work in manufacturing. And where do people go? Do people go to education and health? Where do they go? Well, they go to all of them, okay? If you look at the results, you can compare the numbers, but education go up, health go up, every sector go up when people leave manufacturing. The reason why every sector go up is because we're using a logistic regression where the error term are independent, so we actually don't capture the correlation between these sectors, all right? So manufacturing people leave manufacturing, go to other sectors. Now, okay. All right, so here's a nice summary, okay? So manufacturing go from 21 to 16%, and the retail increase, education increase, the employment share of every other sector increase. What's interesting here is we can calculate what changes to people's utility level, right? Because remember, we have this expected utility we have calculated, which is people's expected utility before they're receiving their random shock. And now we can calculate that again. We calculate people's expected utility again when manufacturing has a lower wage now. And we can compare the expected utility before and after this trade liberalization, or before and after this sudden event. And let du be the difference between utility. So we can summarize the du, okay? It turns out that looks like everybody's utility decrease. Everybody. The mean utility decrease is negative 1587. The highest is negative. So why does everybody utility decrease? Because here I assume that people make choices of their jobs. So when here the assumption is people have observed X, and then they receive a shock E, and then they make their choice. So after they receive a shock, they choose which sector I want to go. But before receiving that shock, Okay, people's expected utility is what we calculate here. So before receiving the shock, if the manufacturing wage has already declined, then it affects everybody. So everybody's expected utility decrease. But whose expected utility decreased the most? Well, we can take a look at the DU as a function of gender, and we can see that male has a significantly larger decrease in expected utility than female. So in other words, this declining manufacturing wage affects male much more than female. Does it make sense? Yes, because typically males are much more likely to work in manufacturing. If we also look at the relation between DU and education, we see that, look, everybody's utility decreased, but it's mainly the people who have education level between 14 and 17, right? So who are these people? These people are the people who have some college education, because if you graduate from college, your education level is 16. Okay, 16 is where you graduate from college. So the people who suffer the most from declining manufacturing wage are the people who have some college, right? They graduate from high school, they have some college experience, but they don't have really high education level. So they have like medium education level. These are the people who suffer the most from this declining manufacturing wage. Does it make sense? Yes. Because why? Because if we look at the original data, all right, what is the education level of all the sectors? Well, manufacturing sector actually has a medium education level, right? The lowest education level, if you do not even have a college, if you do not even have a high school degree, you tend to work in personal service or retail, all right? But if you have really high education, you tend to work in sector like professional services, okay? So if manufacturing wage decline, who are the people that it hurts most? It tend to be the people who have medium, like some college education, who are hurt most. So in summary, men who have some college education tend to be the group that is hurt most by this declining manufacturing wage. So that's the summary result of a very simple analysis. Does it look like a reality? Well, I say yeah, it looks pretty much like reality. So even if our model is extremely simple, overly simplistic, not realistic, it still captures some essential way that the reality operates, right? So this is a very nice result. So like I said, all these results, all this utility calculation depends on you believing the utility interpretation of your model. If you do not believe in it, then it's simply a statistical model, okay, logistic regression. But if you believe in the utility interpretation, then it becomes a simple rudimentary structural model where you can use it to do normative analysis like this and to do counterfactual prediction, okay? All right. Okay, another example, right? Now we're going to again do the catch-up example. 4 brands. So previously I have already done this using probability regression, right? So now what I'm going to do is I'm going to do the same thing but using logistic regression instead of probability. The difference between logistic and probability, like I said, is that logistic regression assumes that the utility essentially is IID Gumbel, so that all the error terms are independent. In this case, it means that the logistic regression assumes that all the brands are independent after conditioning on price. Okay, so this is our results for logistic regression. I will not go into it. I will not go into detail. But this is what I'm going to do. I'm going to again do a counterfactual experiment. Okay, right. So I'm going to predict what happens if Heinz increase price by 20%. Suppose you work for Heinz. Okay, so you're an analyst who works for Heinz. You want to know your boss wants you to analyze what will happen if we increase our price by 20%. How much people will decrease consumption of Heinz, right? Presumably, people will buy less Heinz because our price is more expensive. But how much? What is the elasticity, right? Okay, so let's do this. We make Heinz 20% more expensive. Okay, just change the data, right? Our original data. I don't want to go back for the original data, but in the original data, Heinz has all the price. So all we need to do here is just change the price to make them 20% more expensive, and then I make the prediction again. Okay. The only difference now is I'm going to make the prediction using either logistic regression or using probit. And I'm going to compare that difference, okay? The difference between probit regression and logistic regression. What we can see is for logistic regression, it predicts that once Heinz becomes 20% more expensive, the market share for Heinz becomes 37%. What is the original? Oh, here's a summary. Right? Here's a nice summary. So before the 20% increase, in the real data, Heinz has 51% market share, and the other three has 25 and 22. Okay, so that's the original market share in the original data. So using our model to do counterfactual prediction, we would predict Heinz market share to drop down to 37%. So that's very similar for both logistic and probit. However, for logistic regression, Heinz is 29, for probit is 32. Their amount is 6, for probit is 7. And a store brand for logistic is 25%, but probit is only 22. So you can see the difference between them is that the probit regression the probit model predicts a higher increase. So when Heinz become more expensive, people will leave Heinz, right? People will buy other brands. But what other brand do they switch to? For probit model, people will switch more to Heinz and Del Monte rather than store brand, right? Okay. But for logistic regression, it predicts more people switch to store brand. Which one makes more sense? Well, we know that Heinz and Hans tend to be the more expensive brand. So they are more likely to be substitutes. And in any case, all three of them, okay, because all three of them are brand names, so they're all more, they're all a little bit more different than store brand, right? Store brand is the cheapest. There's no brand at all. It's just made by the supermarket itself. So probit captures this feature. Okay, probit captures how closely, how much these brands are similar to each other and not similar to each other, and essentially predicts that consumer will switch to Heinz and Del Monte more than the logistic regression would predict. So for logistic regression, it predicts more people going to store brand, which in this case should be more unreasonable because store brand is much more unlike the Heinz, right? So if Heinz become more expensive, people who typically purchase Heinz will more likely to switch to other name brands rather than buying store brands. So in this case, I would say the probit regression results look like more reasonable than the logistic regression. And the reason why is probit captures the variance covariance among these different brands, but logistic assumes they're independent, right? So this is another way of explaining the IIA problem facing logistic regression. Okay. Now let's do the mode of transportation, all right? We typically previously did this mode of transportation for logistic regression when we say what happens when we take away subway. Okay, so we have subway, car, bus, 3 different options. When using logistic regression, if we take away the subway, people will spread evenly, or not evenly, but many people will switch from subway to car, and many people will switch from subway to bus, right? What happens when we use probit regression? Okay, so now I'm going to estimate the exactly same data, but now using probit. All right, let's see. Here is the result, and from this result we can see. Hold on. All right. Now, here is our result for the variance covariance matrix. Because once we estimate probit, we can estimate how the different choices are correlated, right? So it's very clear that subway and a car are negatively correlated with each other, and the subway and a bus are positively correlated with each other. Okay. So that tells us that subway and a bus are more similar to each other. Subway and a car are less similar with each other, according to this probit regression results. And that variance covariance matrix has significant impact on how we make predictions in counterfactual world. So now I'm going to take away the subway, all right? And I'm going to use probit and a logistic to make predictions. Here is the result. We already see this result from logistic before, right? Bus, car, subway, take away the subway. The logistic regression says bus will increase from 22 to 38, and the car will increase from 31 to 62. And then we already said that doesn't look like reasonable. But if we do probit, what's the result? Bus will increase from 22 all the way to 60, and the car will only increase from 31 to 40. That looks like much more reasonable to me, all right? So the majority of people who took subway will switch to bus rather than car if we use probit regression that captures the variance covariance among all these different choices. Okay. All right, so that's it. All right, so that's our discussion for the classification and discrete choice model. By the way, in the end, I should say when I give these example, it looks like I'm saying that probe is a better model than logistic because it captures variance covariance. Well, in a certain sense, it may be true, but oftentimes the probe does not perform very well because why? Because the probe relies on numerical integration of normal distribution. So once you have many choices, you have a huge variance covariance matrix that is numerically extremely hard to integrate. So the probe results tend to get worse once you have many categories. And logistic regression, because it has a closed form solution for the choice probability, is always fast and stable. All right. So if you are not concerned, so the lesson here is that if you are concerned that your choices have some variance covariance pattern, have some substitute versus non-substitute pattern that's not captured by your X, then it's a good choice to do probing. If you believe that your choices in your model is relatively independent, then do logistic. Okay, don't do probing. Okay, all right. Finally, as a summary of this whole lecture, right, we introduced classification, the idea of classification, as being done in both econometrics and also data science. Right. So it's the same underlying idea. We need to classify Y into one of the several categories. In economics, the categories tend to be people's choices, often are people's choices, because in economics, we analyze choice a lot, right? So we often use these classification models to analyze discrete choices when people are choosing between A, B, C. In computer science, in statistics, people use this type of model, classification model, to classify anything, okay? To classify whether it's a tree or a dog, to classify all these different classes. In economics, a major use of classification model is to model people's discrete choice. That's why I combine them into a single lecture called classification and discrete choice models. That's the first point. The second point is there are many ways to go beyond what my lecture, right? Because the materials I present here is only a scratch of the surface. Oh, sorry, no, that's not the right word. It's only the surface of the iceberg, right? That's sorry. Okay, so the econometrics, especially in industrial organization, the modeling, analyzing people's demand function, like how do people demand different things? Do people demand Toyota versus, like how to analyze the demand for Toyota versus Honda has been done. There's a huge literature with many different methods being developed, right? A lot of them are based on discrete choice models, because when consumers are choosing between different brands, it's a discrete choice problem. So many techniques or many models go beyond what I present in this lecture, all right? If you're interested, Mu Qing, I've already asked Mu Qing to present to you some more advanced models in econometrics that people have used, especially in industrial organization, to analyze demand and to analyze the market share using discrete choice models. So if you're interested, please go to his recitation. Okay, and finally, because we have already ended our lecture here, we have a new homework, right? Now, starting this week, okay, starting with the classification lecture, I'm going to have something what I call challenges. So previously, for the last two homework, foundation and regression, you are required to just write a report, right, on whatever topic you're interested in. For this one, it's still the same thing. You can write whatever you're interested in. However, if you're willing, this is like a challenge. All right, great, love it. For this lecture, if you're willing to, you can do the problem that I write here. It's called homework challenge, okay? So if you're willing to do this, you can earn extra points. Now, extra points are 4. What does it mean? It doesn't mean that if you do this problem, you get 4 extra points. It means if you do this problem, you could get 4 extra points. You may get 0 extra points, right? But, it depends on how good you do. So here's the thing. In the random utility framework, which is the discrete choice model I just described, right? Each individual make choices independently, okay? So the UIK being a function of observing the visual and alternative characteristics. Now suppose we are studying a problem in which several individuals are making decisions together, and each individual decision could impact other individuals. Okay? So imagine that scenario, right? So in the discrete choice model I just described, when each individual making choice, the choice only impacts that individual itself. So the individual only needs to consider the X variable, right? But if several individuals are making choice together and one person's choice affects other person, then what kind of model is that? You have all studied that kind of model, where individual choice affect each other. And they are making decisions simultaneously, for example. What kind of model is that? That's a game model, right? Do people remember, right? Game theory, right? Okay. What is a game theory? What is a game model? A game model is people making choices together, and their choice affects each other, so that when you are making your decision, you have to not only consider exogenous variable like X, you also have to consider what other choices other people will make, right? You have to consider their strategy in making your own decision, right? So in this case, your Uij is no longer only a function of Xij, some exogenous variable, but it's also a function of the strategy of other people, right? Or expected action of other people. So that's called a game, but so that's a basic game model. And if everybody is choosing between A and a B, or C, okay? So if everybody's choosing between one of the discrete choices, then this is called a discrete game. Discrete game. So this challenge is asking you to basically try to simulate and estimate a discrete game, not just a discrete choice model. Discrete choice model is there's no interaction, but in discrete game, people are interacting with each other in a strategic way, and it turns out that you can, using very similar tools, to analyzing discrete game. Okay, example. The first example is movie theater. Okay, movie release date. Now, when film studio is deciding on, suppose you have your film studio, you have already made a big film, a Marvel film of a superhero, and you are DC, you're also making a film as, also superhero. You want to decide what date to release your film, and that is strategic, because if the two major studios release at the same time, everybody suffers, right? So you want to release at a different date. So, but everybody wants to be at the hottest, like summertime or maybe Christmas time, when all the people are coming out to watch movies. So everybody wants this hot slot, but you also want to avoid being the same time as other people. So that's a typical strategic interaction, right? Okay. So how do people make a decision in that case? When people make a decision, when they make a choice, suppose you want to choose if I want to release in July, or I want to release in August or October, right? Which choice do I want to make? I have to have my utility function. That utility function depends on the market characteristic and also depends on the action of my competitor. Right, so that's a discrete game. How do we analyze that? Well, Einov has a very famous paper on that topic. So if you're interested, you can read his paper on how to use essentially discrete game models to analyze distribution. Right? Example 2, firm entry. So when a firm decides to enter a market, it could just be individual choice, discrete choice, enter or not enter. But typically, a firm has competitors. So when it decides whether to enter a market, it has to consider whether my competitor will enter the market or not in the future, or maybe simultaneously. So that's also a strategic consideration, which it calls for the use of discrete game models, right? So this is a very nice paper by Jia, which essentially models, Pan Jia, which models how whether Walmart and Kmart decide whether they want to enter a local market or not, okay, in an interactive model. So here's the challenge, right? The challenge is, can you do a simple discrete game model involving several players and estimate their utility parameters from data? So you're asked to read. So basically, you're asked to simulate the model in which people have their based on their utility function. People have their optimal strategy, and then they will choose to take action A or action B. And then from your generated data, your generated data is the choice people make, right? And from those generated choices, I want you to estimate the utility parameters back from the data. Okay? So if you are able to do that, you have successfully used a discrete. You have successfully engineered a discrete game model. All right. Now you say, how am I supposed to do that? I never know anything about it. Well, of course. So there are some papers you can read. There's also a very nice summary of the whole discrete game literature. You're welcome to read the paper here. All of the papers are in my materials folder. So if you go to materials for materials, classification, discrete choice models, then you can find these papers here. Okay, just read them. And also, if you go to notes and resources, here I say student contributions. So these are contributions from students from last time I taught this course, and these are what I consider to be very well done paper. Oh, sorry, contributions. Okay, very well done projects. Two of them actually do exactly the same thing, but using R and Python. But for this one, okay, Yu Wei Zhang, she actually did a Battle of the Sexes, which is a discrete game, and she actually tried to estimate that. She was not really successful, but her effort is very nice. Okay, so you can check out her effort in this contribution. There's also this one is also by students because they have the PDF file. I put it here. It's called Estimation of Discrete Game, and it's a realization R. So again, you check out what these students have done and see if you can make better contributions than they did. Okay, so that's it for today, and I'll see each other next week.